relay is a simple electromagnetic switch used in many circuits in transit bus electrical systems. The main relay function is as a remote control switch, where a component controlled by a relay can be energized by a switch very far away. In operation, the relay uses a small current control circuit to control a larger switch circuit. Transit bus relays are known as changeover relays because they change from one state to another, or from a state of being off to a state of being on. In the near future, most relays will become obsolete. For the time being, though, there are millions still in operation on transit buses. Specifications for the relay is best found on the relay itself. Most good relays will have a diagram and also specifications stamped into the housing. The view on the right shows a Bosch relay, and it has 12 volts and also 30 amps, so it gives you some indication as to the capacity or the capability of that relay. Terminals. The terminal 86 of the relay is the power supply for the coil. Terminal 85 is the ground for the relay coil. Terminal 30 is the switch common. This terminal is the one that will supply power or ground to terminal 87A when the relay is off, and to terminal 87 when the relay is on. Terminal 87A is connected to terminal 30 when the relay is off or not energized. This is known as the normally closed side of the switch. Terminal 87 is connected to terminal 30 when the relay is on or energized. This is known as the normally open side of the switch. In operation, current flows through two separate paths in the relay: the control and the switch circuits. The control side is the low amperage side of the relay. The switch side is the high amperage side of the relay. The control circuit is comprised of terminals 85 and 86. Terminal 86 in the case of this diagram here is controlled by a switch. This switch is getting power through a fuse from the battery. Okay. When the switch is closed, it sends voltage or power to terminal 86, goes through the coil, and then out to ground. The switch circuit contains two sets of contacts: a normally open set, terminals 30 and 87, and a normally closed set, terminals 30 and 87A. When the relay is energized, it moves the normally open contacts closed and the normally closed contacts open. And this is the changeover that we were talking about earlier. This is why this is called a changeover relay. So in operation, you'll see that when I hit this switch, I close the switch, current flows through the coil. It moves the contacts from 87A to 87, and my horn sounds. So in other words, I close the switch, voltage flows through here, terminal 86, through the coil, out to ground. Whatever power is waiting at 30 now gets switched to 87A. It goes here to the horn, my horn sounds, and then of course on the other side I have ground. So in operation, the coil creates a magnetic field that pulls this magnetic switch close to 87. When power is removed, the magnetic field collapses and the switch is returned to 87A through a little spring, internal spring. The schematic drawing for a relay is similar to this. This is a generic sample. Depending on the manufacturer of your bus, you might have slightly different drawing, but it is always shown in its off state. So whenever the drawing is, it'll be in its off state. So in the case of this one, there's no power flowing to the coil. terminals 30 and 87A are connected together, which is the normally closed side of the switch, and 30 and 87A are not connected, which is the normally open side of the switch. Relays, like any other coil, create a voltage spike. So when the magnetic field collapses, when power is interrupted and the magnetic field collapses, it creates a voltage spike coming out of the negative side of the coil. Now this spike could be in the hundreds of volts. To suppress or quench this spike, a resistor or diode is placed in parallel to the coil. In reality, you don't want this spike to be circulating through the electrical system and possibly damaging some components, so it needs to be suppressed, and a diode or a resistor is used for this reason. These drawings here, this one here is the drawing of a relay with a diode. So terminal 86 here gets power. Power flows through the coil out of terminal 85, which is ground. When I remove power on 86, the magnetic field in this coil collapses and comes out of the negative side. We don't want this transient spike to go through the electrical system, so we put this diode here to allow it to kind of circulate here and take that voltage down to zero. And the same thing applies to the resistor that is placed in parallel here to the coil. So how do we test relays? Well, the most common test is done by checking the resistance. This implies, or this means, that you would have to remove the relay from its socket in the vehicle and then check the resistance. Okay, so the first thing we're going to do is check the resistance of the coil. So we're going to place our meter between terminal 86 and 85, and for a 12 volt relay the resistance should be between 70 and 100 ohms. For a 24 volt relay it would be slightly higher, between 230 and 280 ohms. The next part of the test is to test the normally open side of the switch. So we're going to place our meter between terminals 30 and terminals 87, and our meter should read OL, meaning that there's no contact between these two terminals. The next part of the test is to test our normally closed side of the switch, terminals 30 and 87A. And when we do that, our meter should read continuity or very close to 0 ohms. In the case of this one, this relay was actually bad and it was reading OL through the normally closed switch. One additional test that needs to be done here, because so far this is just a static test, is to power up the coil and actually see if the switching happens between terminal 87A and 87. You have to go get a battery, put some jumper wires to terminal 86 and to terminal 85 and energize this coil and see if the switching happens. I'm a little bit lazy, I don't like to do that, so I just like to check the relay while it's on the vehicle. So to check the relay while it's still on the vehicle or in operation, the first thing we want to do is to ensure that we have power at terminal 86. In the case of this, I've put my meter black lead to ground, the red lead to terminal 86 by back probing it, and I have 12.48 volts, which means that I have power coming through this fuse, through the switch, and onto the coil. The next thing I want to check is to make sure that terminal 30 also has power. Okay. In the case of this, it does. I got 12.48 volts. The next thing I want to check is to make sure that the voltage that is available at 30 is switching over to 87. In the case of this, it is. I got 12.48 volts. So if I got power here, my coil is going to energize. If my switch is good, it's going to switch from 87A to 87. The power that is at 30 is going to then go to my horn. My horn is going to sound and everything's okay. If I don't have any of these readings, then I have to do some additional testing. The reason I like to check it this way is because I'm checking the entire circuit, not just the relay. The one additional test you want to do is you want to make sure that you also check that your that your ground, terminal 85, and terminal and the connector after the horn, you want to make sure that they have 0 volts or very close to 0 when you check it. So terminal 85 and the ground after the horn should be almost at 0. Now there are relay test kits out there. These test kits make it easier for you to check the relay while it's on the vehicle. So in essence, you pull the relay out, you place this tester in between the relay and its socket, and then you have terminals that you check without having to back probe. On certain vehicles, it's very hard to back probe the relay, so these adapters come in very handy. Well, I hope this short video helps you a little bit. Thanks for watching.